Hi, everybody. I'm Huang from ASU. Today, I will introduce our work, PCR-Auth solving authentication powder challenge with the encoded palm contact response. The authors are me and my advisor, Dr. Chen Wang. Biometrics such as faces, fingerprints, and irises have been widely deployed to verify users. However, due to the increasingly advanced recording technologies, 3D printing, wireless eavesdropping, and malware, the user's biometrics are under two major replay threats, which are the physical forgeries and authentication data reuse. Addressing the replay issues has become a critical task for ensuring the biometric security. And one solution is liveness detection, which requires motions to prove the live faces or leverages heat maps to detect live fingers. While these methods either require the user's participation or are subject to additional sensor overheads. And to further address the data replay issues, behavioral biometrics are integrated with the change response protocols. Specifically, the user is required to respond to a random challenge for authentication by tapping, speaking, or eye tracking. However, existing biometric challenge response solutions all require active participation from the user, which are both time-consuming and intrusive. Instead, this work aims to develop a biometric-based challenge authentication system for the handheld devices, which not only solves the replay issues, but also requires no human efforts. And we propose to leverage acoustic signals to interact with the gripping hand to capture biometric features. After being generated at the speaker, a portion of the stimulus signals goes through a direct path to reach the smartphone microphone. And in addition, some signals go through more complicated reflected paths. And the speaker sound induces the device surface to vibrate, which further creates the sound at the same frequencies and also the harmonics. And as a result, the signals received at the microphone contain three major components, which are the direct path sound, the reflection sound, and the surface vibration sound. When the user holds a mobile device by hand, the contacting palm on the device surface would exert the interference on all the three signal components in form of absorption, reflection, damping, and refraction. And the second equation explains how the three signal components are influenced by the user's contacting palm regarding both the amplitude and the phase. And we then define the palm contact response, which is the PCR, describing the gripping hand's biometric with three signal components regarding the signal frequency. And due to the user's distinctive physiological palm characteristics, such as the hand geometry, as well as the behavioral characteristics, such as the graphic strength, the same speaker sound will result in different sound at the microphone corresponding to different palms. To choose the feasibility, we play a short chirp signal using the smartphone speaker. The right figure shows the received signals at the microphone when the smartphone is held in the user's hand or placed on the table. And from the comparison, we observe that the user's gripping hand suppresses the speaker sound by an average of 3 dB. Moreover, when the chirp signal switches from the 18K to 22K Hertz, the signal amplitudes are degraded with different scales. And furthermore, we found while the direct path signal sound dominate the first 25 milliseconds, the reflected sound and the device vibration sounds became significant after the speaker sound stops. And we then studied the feasibility of using PCRs to distinguish users. This figure shows the spectrogram of the received chirp signals when two users grab the same smartphone twice. And it is evident that the time frequency images are consistent for the same user, but are distinctive among different users. And specifically, not only the dominant direct path signal, but also the sounds after it shows distinctive patterns among the two different users. The results indicate that we can leverage the temporal and frequential information to achieve robust user authentication. We now present the change response model. The PCR encoder is created for each user, which is pre-trained with all of the user's hand grip biometric features. And when the user sends an authentication request, PCR-Auth generates a one-time challenge, and the handheld devices place a one-time challenge encoded stimulus signals using the smartphone speaker, and in the meanwhile, its microphones record the signals to obtain the encoded PCR. Next, the PCR applies the PCR decoder to verify the code and make the authentication decision. And we then introduce the flow of our system. Upon each authentication request, the PCR encoder first detects whether the device is under intentional ultrasonic interference. If not, the PCR encoder generates a one-time challenge and selects the ultrasonic process accordingly to encode the user's hand grip biometric into a PCR code. The microphone data is the input of the PCR decoder. After being pre-processed, the data is fed into the channel filtering-based PCR code extraction to pick up the PCR digits from the audio. And in particular, we derive the spectrogram to capture the PCR code in both time and frequency domains. And the one-time change control channel filter sets a cutoff frequency to extract each PCR digit. The obtained PCR digits are then sent to the CNN-based PCR decoder for verification, where the CNN scores are returned. And we further develop a cluster-based method to verify the PCR code by integrating the CNN scores as well as the SNRs of all the PCR digits, which examines both the user's biometric features and the coding sequence. The access permission is granted only when the PCR code successfully recovers the one-time challenge. For the PCR encoder, we designed the stimulus signals to be a number of 25 milliseconds long and 350 Hz wide chirp pulses within the range of 17K to 22K Hz. We select 10 exclusive layer band channels from this range to represent decimal digits. And the bottom two figures illustrate the stimulus signals for encoding a 4-digit PCR code, where as many as 10 to the 4th power PCR codes can be generated. The raw audio data is first pre-processed, and a bandpass filter with the passband 17K to 22K Hz is used to remove the noises outside of the stimulus signals frequency range. And synchronization is performed by leveraging the evenly spaced chirp pulses. And because each PCR digit is encoded onto one of the predefined channels, we use the bandpass filter to extract each PCR digit by scoping down the corresponding channel. We then derive the spectrogram of each PCR as the biometric features to describe the PCR in both time and frequency domains. In order to balance the spectrogram resolution and also the decoding algorithm complexity, we divide each PCR spectrogram into 3 pieces, which separately describe the different stages of the PCR. And specifically, the first spectrogram mainly captures the pulse impact on the direct path signal, while the second and the third focus on the reflected signals and the induced surface vibration sounds. We use CNN to distinguish people's hands from each PCR digit. The spectrogram of each PCR digit is taken as the input, and the output are the CNN scores, which are basically the user and non-user probabilities. Since each PCR is divided into 3 consecutive pieces, and each smartphone has 2 microphone channels, a PCR digit can be decoded into 12 CNN scores. And next, we develop a cluster-based method to verify the PCR code by integrating the biometric features as well as the coding features. The proposed clustering algorithm explores the relationships between the PCR digits rather than treating each digit alone. This figure illustrates the 2D clustering results. We observe that the user's cluster is clearly separated from the other users, the fake silicon hand, and different replay attacks. For the experiment, we experiment with 6 different mobile device models, which all have 2 microphones embedded. And we recruit 40 participants and collect the data in 2 sessions at different dates, with the first session being used for training and the second for testing. And in each session, the participant is asked to re-grab the phone from the table 40 times in order to include the behavioral inconsistency. This table presents the overall performance of the selected channels when microphone 1, microphone 2, or both microphones of a Samsung S8 phone is used. We found that the 40 participants' PCRs are distinguished clearly on the 10 channels, achieving an average of 91% accuracy when 2 microphones are used. We thus choose the 10 channels for decimal encoding. We now present the performance of PCR-Auth with different code lengths and compare it with the naive decoder, which treats each PCR digit alone. The left figure shows the user verification accuracy when 1 to 6-digit PCR codes are used respectively. We can observe that when using longer PCR codes, the performance of the naive decoder decreases drastically because it requires all the PCR digits to pass the verification, while the accuracy of our cluster-based PCR decoder increases. And the ROC curves of the 4 and 6-digit PCR codes in the right figure further confirm the high performance of PCR-Auth. We then studied our system performance under noise, including daily noise as well as the dedicated ultrasonic noise, which are all measured by the ultrasound pressure level. The figure on the left shows our system works well under these noises, where a 6-digit PCR code can still achieve a 93% accuracy under the 50 dB ultrasonic noise. We thus choose the 50 dB as the threshold to detect the denial of service attack before running the authentication. And it is important to note that some pressure levels of daily noises are always under 30 dB in the ultrasonic band, which means our system generally works for most scenarios. And the figure on the right compares the performance of our system with the traditional method without coding under the side channel replay and the software level replay attack. We found that without coding, the traditional biometric method suffers from 87% false acceptance rate. Even encoding the biometric with a single decimal digit could reduce the FAR by a factor of 10. We further considered 2 new types of synthesis attack where the adversary listens to each coding chirp during the authentication and simultaneously sends the corresponding malicious signal to launch the attack. We first simulate the synchronization disturbance attack by replaying the user's PCR digits with double nothingness, which postpone the entire synchronization to pick up adversarial digits. The figure on the right shows the system performance under this type of attack. As the attacker has to listen and then attack, the delay is unavoidable. We thus consider the entire adversarial PCR code sent with different delays. We observed that when the attack data are included in training, the FARs of a 6-digit PCR fall to 0% for all cases. We then simulate the adversarial perturbation attack by using the perturbation noises to modify the original speaker into the user's PCR digit. Due to the delay, the attacking sound can only modify partial frequencies. The attack has 2 cases depending on whether the perturbations are synchronized well with the speaker sound, as illustrated by the left 2 figures. And the figure on the right shows the system performance under this type of attack, where different synchronization errors are considered. We can observe that when the attack data is included in training, the 6-digit PCR code can also achieve the 0% FAR for all cases. And to summarize, we propose a solution to address the replay issues of biometric authentications by integrating a coding technique with biometric acquisition. We extract the user's hand grip biometrics via acoustic sensing, which is a combination of the physiological and the behavioral biometrics of the user's gripping hand. We encode the user's biometric into biometric code and develop a CNN-based algorithm to decode the unique biometric code. We also investigate the new attacks by assuming the adversary can repeat the code, replicate the biometric, or forge both. And thanks for listening. Please be free to ask any questions.
Thanks for the talk, Long. So there is a question from Hopin by Daming Yang. How does PCR handle those devices having built-in echo cancellation design, which discard the echo of stimulus signals? Does PCR-Auth require specific type of devices?
Yeah, actually, we have not tested the device with echo cancellation, but to my knowledge, the echo cancellation is mainly designed for the audible band, but our system using the ultrasonic sound. So we will try to test those devices. Maybe our ultrasound would pass their cancellation algorithm.
So there's a question on the mic. Please go ahead.
Hi, this is Jianliang Wu from Purdue University. It's a nice talk. So my question is, does your system require the user to hold the phone in a specific way? Like sometimes I hold my phone with my left hand, and sometimes I hold my phone with my right hand, or sometimes I hold my phone with both hands. Does that affect the system?
Yeah, actually, it's a very good question. So if the user wants to use both hands, he has to train the both hands to our model. And in order to include the behavioral inconsistency, which is that users could hold the phone in different postures, we just collect the data by asking the user to re-grab the phone from the table 40 times. And in that way, the user could, there could be differences when the user re-grab the phone. So by doing that, we include the behavior inconsistency. And for some other scenarios, like if you are sitting or lying down, that may need more training data for to make the system work.
Great, thank you.
You're welcome.
Alexei Nogin, Red Balloon Security. So I was just curious, so you've mentioned as one of the factors affecting the sound is amount of fat, so I was kind of curious, do you have a sense of how much it might get confused by users gaining or losing weight?
I didn't quite get that. Can you repeat
you mentioned that the kind of the shape of the reflected sound is among the factors is amount of fat in the hand.
Yeah.
So if the user loses weight or gains weight, and so there is now more fat or less fat, do you have a sense how much of a problem that might be?
Yeah. That's also a very interesting question. So if the user loses weight, I mean the hand size or the fat in the hand may just change. So in order to do, by solving that problem, we may need the user to retrain the model for a period of time, or another solution is if we already know the user's biometric, if we already know the user already logged into the system, logged into the smartphone, and we can, we know the identity of the user, but in this period, we can just launch the training process to update the model to gain the user's most recent hand grip biometrics.
Thanks.
You're welcome.
That will be like a password change. You change your biometric over time.
You mean?
It will be like a password change. Like you log into a system and then you change your password. Here in this case, you retrain the model with the new hand. So one question I had about in slide 14 where you show these different clusters. I might have looked at incorrectly, but it seems like the fake hand and the other person's points are overlapping. So I was just wondering, is the fake hand is applicable for some people? It can be
since the fake hand we use is a fake silicon hand, which is very similar to a real human's hand. So that's why the cluster of the fake silicon hand is very close to the other user's hand. So, I mean, the fake hand shape and also the size is very close to human hand.
And can you speak a little bit about this registration process, or how much time does it take, what the user has to do, and do you need additional device, or everything can be done on a mobile phone for during registration? Yeah.
So for a specific device, the user only have to conduct the experience for training, for 40 times. I mean, grab the phone 40 times. Then that is all we need for register the user.
Do you need to? You don't need any kind of additional training?
You mean the
CNN?
Data? Yeah, actually, you mean the data from other users, or?
So the phone has to do more training, or?
Yeah, we train the model offline, so that's why during authentication, it just launched the decoder and verify whether the user
Okay.
is legitimate or not.
All right. Well, let's thank the speaker one more time.
Thank you.